All right, so if you look at your in-class activity, one of the questions I'm going to ask you is, when I give you a starting material and a reagent, will the reaction mainly be SN1, SN2, E1, or E2? So you have to pick between all four potential reactions. And we're going to break this down into some simple steps. So the first thing I look at is I look at my reagent. And the first set of reagents we're going to look at is going to be a good nucleophile and a bad base. All right, so if we think about examples of things that are a good nucleophile but a bad base, they normally have a negative charge because good nucleophiles tend to have negative charges, but they don't want to steal protons very badly. Does anybody remember what examples fall in this category? Halides, right? So we could have the chloride anion. That's a really crummy base but decent nucleophile. We could have bromide. We could have iodide. And then the last ones were sulfur nucleophiles. Sulfur is kind of odd that way. Sulfur doesn't really want to act as a base because it can also act as a strong acid if it steals a proton. All right, so if we think about this, is this likely going to do elimination chemistry? No, because we simply don't have a good base, right? So not likely to do E1 or E2. In fact, let me slide this over. Not likely to do E1 or E2 simply because we don't have a good base. In order to do elimination, we need to have some sort of base around. We clearly said that these are bad bases. All right, so next what I look at is my substrate. And let's say I have a methyl on one end, meaning my leaving group is coming off a methyl carbon, so it's maybe a methyl halide. Or it could be primary, or it could be secondary, or it could be tertiary. We could even include resonance in here as well. So if we think about what's left over, if we don't have E1 or E2, we're probably going to be looking at substitution chemistry, right? All right. So if we think about this one, we've got competing trends. One reaction's much more likely as we go this way. The other one's way more likely as we go the opposite way. So what's way more likely if we have a methyl group containing some sort of leaving group off of it? Is it going to do SN2 or SN1? SN2. And then over here we said that SN1 is more likely. And we said the reason for this, for SN2, is it's sterically accessible. Where for SN1, we said that this is due to carbocation stability. Let me zoom out a bit. All right. So what we can do is we can start to make general assumptions from this, right? So if we have a methyl carbon, really this is going to do SN2 only. If we have a methyl carbon with some sort of leaving group off of it. All right, if we have a primary carbon, this will also do SN2 only. With resonance, this will likely do SN1. And I'm going to put a little asterisk down here. And I'm going to put unless primary. And the reality is if it's a primary resonance stabilized carbocation, it can do either SN1 or SN2. It's kind of the oddball example because it's sterically really accessible. So it can do SN2 readily, or it can do SN1 because it's also really stable. So it's kind of the either or situation. It's kind of one of the oddballs here. All right, tertiary, we said is too hindered to do any sort of SN2 chemistry. So this would be SN1 only. And then what about primary? Or sorry, secondary. Ooh, it could do either, right? So if we think about the secondary ones, it can do SN1 or SN2. All right, how could we help distinguish whether or not it's going to be SN1 or SN2? Solvent. So if we think about solvent choice, which one's going to favor SN1? Protic. And then aprotic tends to favor SN2. So solvent choice does matter for this in-between one, right? Does this make sense? The intuitive why? This is something we practiced before. All right, let's do the next one. So instead of thinking about nucleophiles, let's think about bases. Oops. Let me change this to good base. Bad nucleophile. Let's come up with some examples of these. What's an example of something that's a really good base but a really, really crummy nucleophile? Hydride. Hydride's a good one. What's another one? DBN. That was our big bicyclic ring system. DBU. Another one? Terbutoxide. Terbutoxide's too bulky to be a very good nucleophile. There was one more. Had another acronym. It had two isopropyl groups coming off of it. It was called LDA, lithium diisopropyl amide. So really all of these are examples of things that don't want to act as a nucleophile. Does this mean that we're likely going to do elimination or substitution? Elimination. Okay, so let's do the same thing where we've got methyl, we've got primary, got secondary, got tertiary, and we've got resonance. All right, so now we need to think about which of these is likely going to do E2 chemistry. What do you think? And I'll give you a minute to think about this and talk with your neighbor. I'll give you another question to consider when you're chatting with your neighbor. Will this do E1 chemistry? Ah. All right, while you're considering that, I'm going to write out a starting material. What happens if we have a methyl substrate with a leaving group and a strong base that isn't nucleophilic? We have no beta carbons. This won't do anything. So I'm going to just immediately rule out the methyl one. And I'm going to write no reaction. Meaning we have no beta proton. All right, what about the primary carbon? So for example, if I take this one where now I've got an ethyl group plus hydride, will this work? Yeah, absolutely. Will that do E1 or E2? E2, why? It's a strong base, right? We said E2, you always have to have a strong base. All right? So if we do this one, we can say E2 only. Why won't it do E1? It wouldn't form a stable carbocation, right? So we could immediately say E1's just never, ever, ever going to occur here. All right? Now let's take another example. Let's do the secondary one, right? So again, I'm just going to draw some examples down here. Will this do E1 or E2? It'll do E2, right? All right, and then we can think about tertiary carbons. Will this do E1 or E2? It'll do E2. All right, what about if you've got a resonance stabilized position with the leaving group? It'll do E2. I think we're seeing the trend. So E2, if it has beta protons. So we do have to make sure that if it's resonance stabilized, it has beta protons. And I'll show you an example of one. What happens if we look at this carbon? This carbon is resonance stabilized. Will this do E2 chemistry? It doesn't have beta protons. So it won't do any E2 chemistry here. That's why I'm saying if it has beta protons, this one will just stare at the hydride and really won't do anything. So it's just going to go slow. All right. Now my second question is, which of these will be fastest, primary, secondary, or tertiary? Tertiary? Why?
Hyperconjugation.
Yeah, exactly. So faster rate. So really, E2 reactions are more favorable the more substituted the alkenes are that we form, right? So let's make a note of that. All right. I did want to talk briefly about the E1 competition. There's going to be no E1 because E2 will outcompete it. Does anybody know the why behind that? What's the fastest reaction in chemistry? Acid-base chemistry. So this first step is acid-base chemistry. That's going to be faster than your leaving group falling off, right? So acid-base chemistry is the first step in an E2 reaction, where it's the second step in an E1 reaction. So it's just simply a competition game we're playing here. Does that make sense? All right. Now we got to get into the next one. Let's do good nucleophile. That is also a good base. And I did want to give some examples with this one too. What are some examples of good nucleophiles that are also good bases? Hydroxide, right? Hydroxide, because it's not sterically hindered, it's a pretty good nucleophile. We could also have other alkoxides as long as they're not too hindered. So we could have methoxide. We could have ethoxide. The key is that it's not a tert-butyl group coming off, right? If it's a tert-butyl group, it's just simply too bulky. Are there any other ones? Yeah, there's some other ones as well. If we think about like cyanide, you could argue that that's a pretty good nucleophile, pretty good base, things like that. So we could think about those as well. All right. So now we're going to do the same trend. All right, before we do the trends though, I want to predict which reaction pathways are going to be more favorable. So the fact that we have a good nucleophile tells us something. What do you think is going to be more likely? Is it going to be SN1 or SN2 if it's a good nucleophile? SN2. So let's write that down. Good nucleophile. SN2 is favored over SN1. Whoops. All right, and then we could say good base. What does that tell us? E2 is going to be favored. Whoop, over E1. All right, so we know that this set is probably going to be an SN2 reaction or an E2 reaction, but we've kind of set the framework for this. All right, so let's start with the methyl one. Is that going to ever do E2? No. So what does that tell us? SN2 only. No beta protons. So that one's pretty easy. What about primary? What do you think's going to occur? Okay, we could say either one, right? Because we know primary carbons can do E2 or SN1. But if we go back up and we look at it, what do you notice about the rate for primary carbons? It's going to be slower. So competition-wise, which one do you think is going to be more likely? SN2. And in fact, experimentally, that is what is observed for primary ones. We'd say SN2 is major, E2 is minor, and the reason being is that E2 is slow for this reaction, right? So it's a slower rate compared to the SN2 reaction. All right, let's think about secondary carbons. What do you think might happen with a secondary carbon? It might be reversed. Or you could argue it's a tie. Experimentally, we normally see that it's reversed. And why do you think SN2 is going to be more minor in this one compared to the primary one? Why would it be slower than with the primary carbon? So if we think about what impacts SN2 rates, sterics plays a big role. This is sterically more blocked. All right, now let's think about tertiary carbons. Tertiary carbons, what do you think will happen with that? E2 only. All right, and then with resonance, what do you think could occur here? And I am going to put the disclaimer, it could be SN2 if primary. So there is kind of this weird hodgepodge that could occur here, right? So it is a little bit confusing. A lot of this has to do with the rates of reactions. So we've got these competitions, meaning both reactions can occur, but we're asking ourselves which ones will occur faster. So really, SN2 reactions occur faster this way. And then we said that E2 is faster going this way. What a lot of students do that I see when they're taking organic chemistry is they try to brute force memorize all of this, which great, that'll get you through the next week, and then come next term, you'll forget everything again, and you'll struggle all over again. So the key, in my opinion, is understanding the why behind these. Be able to rationalize your way through it. Does that make sense? All right, one last one. Whoops, shoot. We've done the good bases, good nucleophiles, good bases that are also good nucleophiles. What if we have a bad base, bad nucleophile? Before we do that, let's come up with some things that are bad bases and bad nucleophiles. Water. Really any alcohol. They're not the greatest nucleophiles, and why is that? They don't have a negative charge. The oxygen's going to hold its lone pairs tight, close to itself. It doesn't want to really give up those lone pairs, so it's a bad nucleophile. And we drink water. Hopefully it's not a strong acid or a strong base. It's nice and neutral, right? So these are the classic examples of bad bases, bad nucleophiles. All right, so let's do the same thing. And let's try to predict which reaction pathway is going to be more favorable for this one. So if we have a bad base and bad nucleophile, are we going to do SN2 ever? No, SN2, we need a good nucleophile. What about SN1? Yeah, we could do SN1. And why is this the case again? Just briefly reviewing. Oops, that should be 2. Why is it more favorable over itself compared to SN2? It's more important to have a good leaving group, and the nucleophile is not involved in the rate limiting step, right? So the nucleophile strength doesn't really matter that much. It doesn't increase the rate at all. All right? And then is E2 or E1 going to be more favorable? E1. All right, so now the question is, what will happen with a methyl carbon with a leaving group on it? Will it ever do E1 chemistry? No. So no E1. Will it ever do SN1 chemistry? Meaning no reaction at all will occur. All right, let's do the same thing with primary. What will happen with the primary one? Probably neither. Oop, that should be SN1. And I'm going to put a little asterisk here. There may be a specific situation where this occurs. What do you think could happen? Let's say you kick off your leaving group and get a primary carbocation. It is really, really unstable. What could happen, though, to stabilize it? Could rearrange or have resonance. We've got resonance already on this table, so we're going to ignore resonance for now. So it could rearrange. However, do you think this reaction would be very fast? No, the rate limiting step is still that leaving group falling off, forming a really, really unstable carbocation. So I'm going to put, but the reaction would be crazy slow. So typically what people will say for this one is primary, while theoretically could occur, it's just not practical. Is that how you spell practical, or is it ACLE? Oh my goodness. No. Oh my goodness. You guys are lucky I don't teach any other class. All right. It's too slow. All right, what about secondary? Can SN2, or sorry, SN1 occur with secondary carbons? Yeah. So I would say, yeah, SN1 is okay, and E1 is also okay. Do you think it's going to be very fast, though? Yeah, so let's make a little note on this. Still pretty slow, and oftentimes people will say, yeah, these can occur, but they're just going to be kind of sluggish, right? Because the rate limiting step is the formation of a secondary carbocation. What will likely occur to that secondary carbocation? Yeah, so let's make a note. Will likely rearrange if possible. All right. So what I will do is say we will get a mixture of these. We will get a mixture of SN1 and E1 with these. Yeah?
Is it the rearrangement that's slowing down the rate, or just making the carbocation?
So that's a great question. Is the rearrangement slowing it down, or is forming the carbocation? We know that the rate limiting step is the leaving group falling off, so it's the formation of the carbocation. That's why with secondary carbons, it's a lot more practical, meaning faster, than with a primary carbon, because that's the rate limiting step, is that leaving group falling off. All right, tertiary carbons, what can they do? Yeah, they can do both. All right, and resonance, they could do both. And I'm going to make a note for E1, unless there are no beta protons, right? We could have some E1 reactions where there's no beta protons. So I'm going to write up here that we'll get a mix, and mix. How could we favor E1 over SN1 for this? Heat. So let's make a note that heat favors E1 over SN1. Whoop. And why is that? Chaos or entropy. We talked about it early on in the elimination chapter. Elimination, we create more moles of product than starting material, so entropically it's more favorable, where entropy doesn't play a large role with substitution. Yeah?
So for SN1 reactions, the nucleophile doesn't look matter. So how come before when it was a good nucleophile at a bad base, E1 reactions could happen? E1 reactions could happen.
So you're talking about a good nucleophile that's also a good base?
No, a good nucleophile and a bad base.
Good nucleophile that is a bad base?
Yeah, so for tertiary and resonance, why couldn't you have?
Oh, because these are bad bases, they're just really not going to be very aggressive about stealing a proton. The acid-base chemistry is going to be slower than the substitution. Okay. So that's the key thing I pointed out, is bad base just means it's very unlikely that it'll do either elimination. We're down here, we said that they're a bad base, but they can still do a little bit of acid-base chemistry. These are better bases than the halides, if that makes sense. Yeah. All right, so heat favors E1 over SN1. All right, the other thing is that secondary or tertiary alcohols plus catalytic acid plus heat will always favor what? E1, kind of like we saw in lab, right? And what's a common catalytic acid that we'll see? There's two, I guess. In lab, we use H2SO4 or H3PO4. These really, really favor E1. They don't favor SN1 at all. So this is one way of favoring E1 over SN1 and not really getting a mixture. Why is that? Why don't we get any SN1 with these? Has to do with the conjugate base of our acid, right? If we think about the conjugate base for sulfuric acid or phosphoric acid, it's resonance stabilized. It's a really, really crummy nucleophile because that negative charge is spread out so much. So going back to what John was saying, I'm going to actually change this a little bit. Instead of saying bad, I'm just going to say weak, meaning it can still do both of these things. It's not that it's bad at it, it's just weaker. Does that help clarify? Yeah. Okay. All right. So really quickly, before we go on to our worksheet, they've got this nice chart in the textbook, but like I said, I really discourage students from brute force memorizing this chart. But you can see on this side, this is your substrate. He trims it down and doesn't even have a methyl group or resonance stabilized. I kind of expanded on that. And then he's got each of the 4 categories that we talked about already. So you can use this chart as you're working through the worksheet, but try to get so used to it that it becomes second nature. So between now and next Wednesday, you should have this down pat. I know it does take a lot of work to do this though, so we're gonna have a worksheet today that you can get started on, and then I'll hand out a new one tomorrow. So if you want, you can spend the rest of this class period working on that worksheet. It's pretty similar to what you might see on the final exam.